We had some questions for homework last night, page 538, number 4 to 10. We want to go over 4 questions on that page. Starting with number 4. It says Coulomb could not measure the amount of charge on his spheres, but he could vary the amount of charge on each sphere, or describe the process or the procedure that he used to do so. So if you remember that torsion balance experiment, basically you got a string hanging from the ceiling with a rod on the end of it. We got a charge 1 right here, and then another thing over here just to balance it out. We bring another charge, Q2, nearby it, and then we find out how much it twists. The amount of twisting is a measurement of how much force is applied. And I think we saw that on a question on the quiz yesterday, right? The amount of twisting being proportional to the force. So Coulomb did 3 experiments, in fact, with this. The first one, he would have manipulated the value of Q1. You saw how the force responded to that. He would have kept constant, or as control variables, Q2 and R. Got a straight line for that. Then he manipulated Q2, saw how F responded to that, keeping constant Q1 and R. He would have got a straight line for that one as well. And then finally, he would have manipulated the value of R, the distance that separates the charges, keeping constant Q1 and Q2. And for this one, he would have got a relationship that looks like this. It's called an inverse square relationship, where as R goes up, F goes down exponentially. These are the ones that we care about right now, because these are the ones that are relevant to the question number 4 that says, basically, look, he couldn't measure the value of the charges. He didn't know what they were in coulombs, but he could do this experiment. He could change the values without knowing what they were. And how do you do that? Well, let's say that you started with Q1. Let's just call it Q, actually. Okay? We want to change the value of Q1. Let's just call it Q. We got another charge over here that is nothing, neutral. And that's easy. He can measure that one easy enough because there's just no charge on it. Bring it near an electroscope. If the leaves don't spread apart, then it's a neutral charge. What's the value on the other one? Don't know. Call it Q. Call it whatever you want. Okay, we're calling it Q. Let's say he touches these 2 things together. When he does, what do they both become? Q plus 0 divided by 2 is half Q and a half Q. Does that make sense? Take this one and move it away. Let's take another charge now that's neutral and touch the one that's a half Q to the one that's neutral. Now we're going to get a quarter Q. Half Q plus 0 divided by 2 is a quarter Q. Let's take this one and get rid of it. Let's create another charge that's neutral and touch it with the one that's a quarter Q. Well, now I touch them together, it's going to become an 1/8 Q and an 1/8 Q. We don't really care about this one. This is just the one that we're using to manipulate the other one, so we'll get rid of it. Bring this one down, bring a new charge that's neutral down, and so on and so on and so on. You can see what we're doing here, right? We're changing the value of these charges. We don't know what the charge is in coulombs, but we know what the relative value is. Go back to this graph for a second. Maybe this is an 1/8 of a coulomb, or sorry, an 1/8 of Q. This is a quarter Q. This is, what would this be? A half Q over here, and a Q over here. You see how we can get all these different values of Q, and we can get a relationship on this graph without actually knowing what the values are in coulombs. Now, that prevents me from actually getting a number for the slope of that graph, but it doesn't prevent me from getting a relationship. And that's all we wanted here, right? Was to determine the relationship is a directly proportional relationship. Does that make sense? Can't find coulombs, but the actual charge, but he can manipulate the charge, basically creating his own units, right? Instead of saying, using coulombs, he essentially creates his own units and says, all right, this is 1, what units do you want to make it? 1 cars. Okay, that's our new unit, cars. Connors, you say? Oh, okay, Connors. So that's 1 Connors. This is 0.5 Connors. This is 0.25 Connors, and so on. right? So any value he calculated would not be standard units for that value for slope or whatever. It would be using these units of Connors that he essentially invented. Okay. Next question was number 5 that we want to go over. It says, the electrostatic force of 10 newtons acts on 2 charged spheres separated by a certain distance. What does the force become if we start doing things to the charges? Let's create a little bit of space for this. So my original force is K Q1 Q2 over R squared, and its value is 10 newtons. Now what happens if I make some changes to it? First change I want to make, the charge on one sphere is doubled, so it becomes 2Q1. The other one remains Q2 over R squared. That becomes 2KQ1 Q2 over R squared. And we know what the value of this is, right? It's 10 newtons. So 2 times 10 becomes 20 newtons. The answer to A would be 20. Now how do we change this for B? Well, we got another 2 in there, right? Because we're doubling both charges now. 2 times 2 is 4. 4 times the original force is 40 newtons. Question number 6. The electrostatic force of, why is it difficult to attain a large charge of 100 coulombs on a small object? I like this question, actually. It's a really good question. Can anybody answer that one for me? I mean, clearly, we know 100 coulombs is a massive amount of charge, right? We said 1 coulomb is a really, really big unit of charge. 100 coulombs is a whole lot of a really, really big charge. So it's really, really, really big. Now do you get it? Yeah, Ian, is it good now? Why is it hard to get 100 coulombs of charge, particularly on a small object? Go ahead. Okay. All right, here's the deal. Let's say we have 2 excess electrons. They're going to repel each other, right? And those excess electrons are going to go as far away as they can. Now, I can't draw a 3-dimensional sphere, but let's say I could draw a 3-dimensional sphere. They would literally be on opposite sides of the sphere, as far away as they could be until they reach a point of equilibrium. Okay? If I put 3 charges on there, they're going to redistribute so that they're as far away from each other as they can possibly be. But you know they're going to be closer together if I have 3 of them than 2 of them, right? You can't spread them out evenly with as far apart when you have 3 as when you have 2. Well, if I have 4, then to reach that equilibrium, spread them as far apart from each other as they can be, then they've got to be even closer together. 5 even closer, 6 even closer, and so on. The more electrons we get on there, the closer they end up being together. Why does that matter? Well, we saw this just a minute ago when we were looking at these graphs here. The closer they are together, the force of repulsion between those electrons becomes, as R gets smaller and smaller and smaller, F gets exponentially bigger and bigger and bigger. So as we get more and more electrons on there to give me more and more charge, 100 coulombs of charge is a huge amount of charge, a huge number of electrons that would be required to do that. The force of repulsion is so massive because they have to be so close together to physically fit that many electrons on there, then you're going to end up having such a big force of repulsion that they're going to push each other literally right off the surface of this. It's going to be easier for the electrons to leave the surface of this metal sphere than it is for them to stay on the surface. Make sense? It's like, you know, you like going to the to an event, right? It's like some kind of a concert or something. You're going to some event, okay, and there's 100 people in there. It's all good, okay? You want to get away as far away from them as you can because they kind of smell a little bit. Maybe not. Maybe you just want your own kind of personal space. As we get more and more people, you get less and less personal space, right? Okay? But you're kind of like trying to get as far away from them as you can. At some point, there's so many people there, you can't get far enough away from them. You're so close to each other that you're like, I'm just going to leave. It's easier for me to leave than it is for me to stay in that situation there. Question? I don't know, actually. I don't know. 6b says during the rubbing process, an object acquires a -5 times 10 to the -9 coulombs of charge. How many electrons did it gain? Remember the orange analogy? You go to the grocery store, and one orange weighs 100 grams. You buy a bag of oranges that has a mass of 600 grams. How many oranges? We all know it's 6 oranges, right? The total mass divided by the mass of one orange. Well, remember with charge, number of electrons, we're going to find the total charge divided by the charge of one electron. So -5.0 times 10 to the -9 coulombs divided by -1.6 times 10 to the -19 coulombs. And 5 divided by 1.6 is 3.125 times 10 to the 10. 3.125 times 10 to the 10. So lots of electrons, right? Lots of electrons giving me a charge of only 10 to the -9 coulombs. Imagine if we had 10 to the 2 coulombs like we did in question A. You can imagine if you have this many electrons that make up this much charge, you got to have way more electrons making up this much charge. And they got to be, like there's so many of them, they got to be pretty close together. And there's going to be a pretty big force of repulsion as a result of that. And that's why we get the answer we got for A. Okay, last question. Number 9, a helium nucleus has a positive charge with a magnitude twice that of the negative charge in an electron. So let's draw this out here right now. Here's helium. There's 2 protons in a helium nucleus. There's neutrons as well, normally 2 neutrons, although not necessarily. There's usually going to be 2 electrons orbiting around as well, but this question relates only to one of the electrons that orbit around. The question basically says, look, there's a force acting on the electron pulling it in. It's an attractive force, right, between the protons and the electron. There's also a force on the nucleus pulling it out. Which one's bigger? That's the question. How do they compare? Ethan? Were you answering the question? So you're saying the force on the electron is bigger than the force on the nucleus? Anybody else? Maybe equal? I'm going to go with Matt on this one. The forces are going to be equal, yeah. And why? Well, Newton's third law says if object A applies a force on object B, B applies an equal and opposite force on object A. The forces are the same. So why is it that the electron is affected more? We know the electron is going, at any given point is going in a straight line, but it doesn't stay going in a straight line. It gets pulled in towards the nucleus, which ends up ultimately making it go in that circle. Then nothing happens to the nucleus, but something does happen to the electron. If it's the same force acting on the nucleus as it is acting on the electron, then why is it that the electron is affected by that force more? Because it's lighter. It's about 1,000 times lighter. Okay? One electron has a mass of 10 to the minus 31 kilograms. One proton has a mass of 10 to the minus 27 kilograms. Okay? So you're going to get, yeah, same force acting on both of them, but you're going to get about 1,000th of the movement of the nucleus as you are in the electrons. It's kind of like the Earth going around the sun, right? There's a force of gravity on both of them. In fact, it's the same gravity. The gravity that the Earth applies on the sun is the same as the sun applying on the Earth. Why is the Earth affected more? Because the Earth is way lighter than the sun is.